let's just move on further, and further we will talk about the nature of the decimal expansions of the rational numbers. I hope we are all done with the chapter rational numbers in the class 9th, and we do know about all the concepts that are related with the rational numbers and with their decimal expansions, how we can call them as terminating as well as non-terminating, because we do know that the rational numbers are of the two varieties, that is a terminating one and a non-terminating one, and further recurring and a non-recurring one. So on the basis of terminating and non-terminating, we can find out the nature of the decimal expansions, that what is their nature, then whether they are terminating or whether they are non-terminating. So let us suppose I'm talking about the very first part. This is 0.875 and the second part is 1.512341458123. So as we can see in the part 1, we have a decimal expansion is 0.875. So such a decimal expansion is called as a terminating one, because the remainder of this type of a rational number is always 0. So whenever the particular remainder of any particular rational number is 0, we can call them as a terminating decimal expansions or terminating rational numbers. So this decimal expansion is nothing but a terminating one, but on the other hand, we can see that the number is a non-terminating one, because it still goes on without the repetition or without there does not exist any string of numbers that are repeating itself. So such a type of decimal expansion is called as a non-terminating one. So the decimal expansions do have two varieties as terminating, non-terminating, and further recurring and non-recurring. I hope you know about such the type of the terminating, non-terminating numbers, because on the basis of that previous knowledge, we will further move on towards the concept in which we will see whether a rational number of the type P by Q is terminating or non-terminating without actual division. So let's just move on further towards the two theorems which are really very important. So the theorem number 1 says that let x be a rational number whose decimal expansion terminates. So it is saying itself that let us suppose we have a rational number whose decimal expansion actually terminates, just like the very first part we have discussed before, and then x can be expressed in the form of P by Q, and then we can express it in the form of P by Q, where P and Q are co-primes, and the prime factorization of Q is of the form 2 raised to the power m into 5 raised to the power n, where m, n are non-negative integers. So what we can conclude from this particular theorem, that if we have any rational number of the type P by Q such that PQ are co-primes, this is our first condition, that PQ should be co-prime. The second condition is the prime factorization of the denominator Q should be of the form 2 raised to the power m into 5 raised to the power n. If these two conditions satisfy, then we can say the rational number should be of the type of terminating one, means we can say the rational number is actually a decimal expansion, or a rational number do have a decimal expansion that terminates. So with the help of this particular theorem, we can conclude whether a rational number is terminating or a non-terminating one. So I hope this theorem will definitely help us to solve the questions which are of the type, or which are of the type P by Q formation, means they are the rational numbers, and we do have to find out that without the actual division, we have to conclude whether they are terminating or non-terminating. So there are two conditions that we can call any rational number as a terminating one. First of all, the P and Q should be co-primes, and the second should be like the denominator is of the form 2 raised to the power m into 5 raised to the power n. Now let's just move on further toward the second important theorem. The second important theorem says that it says let x is equal to P by Q be a rational number such that the prime factorization of Q is of the form 2 raised to the power m into 5 raised to the power n, where m and n are non-negative integer. Then x has a decimal expansion which terminates after k places of decimal. So from this particular theorem we can conclude that any number x, when will it terminate, or after how many places of decimals it will terminate. So we can say then x has a decimal expansion which terminates after the k places of decimal. What is the value of k over here? K is the larger of m and n. So let us suppose we have any particular number in which the denominator of the rational number should be of the type 2 raised to the power 7 into 5 raised to the power 4. 2 raised to the power 7 and 5 raised to the power 4. And if I'll ask you that this particular number do have a decimal expansion, then after how many places it should terminate. So we do know that 2 raised to the power 7 and 5 raised to the power 4. In both of these powers, 7 is the larger of 7 and 4. It means that after the 7 places of decimal, the number should terminate. So this theorem helps us to find out that after how many places of decimal the rational number can terminate. So this is another important theorem which helps us to solve many questions which are of the form P by Q, and in which the question asks us that after how many places a particular, or after how many decimal places a particular rational number can terminate. So this is again an important theorem. So let's just move on further and let's just do some of the questions that are related with these two theorems.